Uh, Hello, dear participants. I am Divya S. Nair, Assistant Professor, Department of Civil Engineering, College of Engineering, Kidangoor. Respected faculty members and research scholars. Today is the first day of one-week faculty development program on modern trends in civil engineering construction industry, organized by Department of Civil Engineering, College of Engineering, Kidangoor. It gives me an immense pleasure to introduce and welcome today's resource person, Dr. Sripriya Rengaraju. She is a postdoctoral research in Cambridge University. She did her PhD from Department of Civil Engineering, Indian Institute of Technology, Madras. She had published many journals and more than 15 conferences. Her research interests include smart infrastructural materials, structural health monitoring, and durability of concrete structures. She had won several awards for her novel research work, which includes RILEM Best Student Poster Award in 2017, ACI Best Poster Award in 2019. She has won Avisor Postdoctoral Award in 2020. IIT Madras acknowledged her scientific contributions with the Institute Research Award in 2019 for the quality and quantity of research work delivered as a part of her doctoral degree. She is very much passionate about her teaching and research. She is currently working on self-healing and self-sensing materials in concrete. I welcome again Dr. Sripriya Rengaraju for today's session. Thank you very much. Over to you, ma'am.
Thank you.
Sripriya?
Yeah. I'm just sharing my screen.
Okay, fine.
I think it is taking some time. Sorry for that.
Okay, no problem, ma'am.
Is my screen available?
Yes, ma'am. The screen is clear.
Okay.
You may please continue.
Yeah. Good morning, everyone. I'm Sripriya. I'm a postdoctoral researcher in the University of Cambridge, UK. So today we are going to discuss about the structural health monitoring, especially in reinforced concrete structures. I will emphasize more on that. This is the brief outline of my presentation. First, we'll talk about what is structural health monitoring, why do we need structural health monitoring, and traditional ways of checking the health of the structure, and how this has evolved into modern methods, followed by a case study where it can be used. What is structural health monitoring? Like how we do our regular health checkup and assess our health condition. Similarly, we do the monitoring of structures. We check the structure for its status. So why do we need this? This is needed for the to ensure the longevity of the structures, and also to take any actions if there is a problem. So structural health monitoring is the best way to ensure the long-term durability of structures. As I told before, this is done mainly to avoid loss of people and property, and it also gives to less economic burden, because if there is a sudden collapse, then there is no option for us to do any other action. It is we have to build another structure. So to have that sudden economic burden, to avoid such kind of economic burden, we need to have a regular structural health monitoring as we do in our health checkup. So this also helps us to identify the root cause of any kind of deterioration, and we can have options to mitigate in case of severe problems. So it also gives a first-hand report in case of major calamities such as earthquake. So for what type of structures should we do structural health monitoring? Tunnels, bridges, skyscrapers, historical monuments, dams, wind turbines. In general, any structure which is of social, cultural, and economic importance, we can do this structural health monitoring. How to do structural monitoring? You can see this is a bridge that is right in front of the CN Tower in Canada. So here you can see that it's in a very bad state. You can see all the reinforcements and how severe the corrosion is. This is due to the leaking of de-aging salts from the surface onto the concrete, and because of that the corrosion has occurred and the cover concrete has spoiled. So how to avoid this kind of deterioration in our structures? It's not only happens in India, it happens everywhere. So we are aware that such kind of problems exist in our structures. So how to do the structural health monitoring and how to assess whether this structure is safe or not? But by looking at the picture, you can see that this is a very bad state. But in our case, in India, many of the structures will not have this kind of visual signs. And so in such kind of cases, what should we do? How to do the structural health monitoring and when to start the structural health monitoring? So we have different ways of doing structural health monitoring. First, I will address how to do, and then I will say when to do. Okay. So the how to do is we can do a traditional periodic health checkup, like as we do for our master health checkup. We have a set of tests, and we will assess the structure based on these tests, and then we will overall put a ranking on how the structure is performing. So first observation, what we do is visual observation. Then whether it is very much damaged, like as we saw in the previous slide, or whether it is okay, there is no visual signs like that. So we will assess based on the visual inspection, and then some of the on-site measurements like rebound hammer, UPV, and then infrared thermography, then crack measurement. We can have a crack meter and do this. Cover depth, resistivity, half cell potential. We have all tools for this. Even in case of a pre-stressed concrete, we have like visualization by boroscope, specialized instruments for monitoring how the wires are performing, and acoustic emission for understanding whether the wires is there any breakage in the wires. And apart from that, NDT test, we can also have a core. And from the core, we can also see what is the strength, whether it has carbonated, whether it has any microstructural changes. So these are the traditional ways. So once we do the traditional ways, we know how much it is deteriorated or not. So these kind of tests will give results only when the condition is manifested. So if there is a health condition, if there is a damage, when it is manifested, then only these entity test and other things will give us a significant warning. Okay, it's not called warning, significant representation that there is something going on. But we want to take steps before this happens. So for example, if cancer is there, the mammogram can help us to detect the cancer, whether it has just started or which status it is in, and we can have precautionary measures before going to the metastatic stage. That is, before moving to the other parts of the body, right? Similarly, we have to take some kind of measures to prevent the deterioration happening from one localized location to the other. How do we address it? There are different methods available. Those are modern methods where continuous structural monitoring is possible. This is enabled by using sensors. So I have listed some of the sensors which we are using in structures today. So the temperature probes. Temperature probes are these are used widely in during construction. So we have different types of probes. One is for concrete, that is how the strength evolves. So many of the times you might have heard we have poured the RMC plant, RMC plant concrete, and it is not setting. So when we do a mass concreting, for example, if we are doing foundation level, raft foundation kind of thing, so when we do such kind of mass concreting, we have faced issues with either setting, or it will have an issue with very high heat of hydration, like a very high temperature evolved during because of the mass concreting. So we can eliminate these two with the help of this temperature probes. How can we eliminate this? Temperature probes will indicate how much is the heat that has been evolved. You know that cement, when reacts with water, is an exothermic reaction. So when these two start reacting, certain amount of heat is evolved. Based on the heat, we can predict how much is the strength. So whether the heat is too much, so what is too much temperature? Whichever is going beyond 70 degrees Celsius, there will be a delayed etching rate formation in the concrete, as well as there will be thermal cracking. So these can be avoided with like how much concreting should be done per day. That can be monitored with the help of temperature probes, as well as when there is a difference in temperature, like climatic changes and things happen, we know that this kind of strength will be evolved in laboratory condition. But will that the same kind of strength evolves in the site? That we do not know. So when we have this temperature probes, we can have this kind of monitoring, and we can predict how much is the strength and when we can expect the next pour, like that. Okay. The second is load cell. Load cell is, you might have used in some of the laboratory applications also, because of there are different types of load cells, and because of the mechanical pressure, the load will be indicated in the form of dial gauge or diaphragm kind of digital. Nowadays, a lot of load cells have come. And then strain gauge. Strain gauge typically they use like the simplest form is the strain gauge, which you stick to the concrete surface, and based on the strain, Wheatstone bridges used, and you can calculate the resistance. Based on the resistance, you can calculate the strain. And then linear variable differential transformers. These are used for measuring the linear distance. So, for example, if there is a differential settlement, or there is a crack formation or crack movement, then this can very well indicate that. Then extensometers. Extensometers also you might have used in your laboratory. This works on the same principle. So at a point, you measure the strain, and you because of that you can indicate how is the strain is evolving in the structure based on the load. Then the piezo impedance transducers, these are very new transducers which are in research mainly. So what happens is when there is a pressure, because of the pressure, there will be a change in the resistivity, and that resistivity will indicate how much is the strain or how much is the parameter which we are targeting. So you might have seen this in roads. When at one stretch of the road will be the piezo electric or piezo impedance thing will be inserted on the road, and when the car moves at a speed, based on the speed, it will there's a portion of the road will have that kind of pressure, and then it calculates the speed of the car. And this is how in most of the foreign countries they impose the speed limit. So even if there is no one, there will be sensors on the road which can capture the speed of the car, and based on that they will fine you. And this is very much applicable for roads, but in concrete we are now in the research stage. We are having like a graphene ink, graphene powder, and we are mixing this in cement and trying out how the conductivity changes based on the strain. So this is very much in the initial stage. We have miles to go in this type of transducers, but this is very promising because it doesn't rely on circuits. So these kind of transducers can go for long-term monitoring, so which is very, very essential for these kind of sensors. Then accelerometers, even in your phone you have accelerometers. So how fast you are walking, that is captured with the you can calculate very well in your phone, right? So these kind of accelerometers are there everywhere. So these in this context, what we are measuring is the movement of the movement and vibration in case of bridges, etc. Then FiberGrating Sensors. These are very high-end sensors, you can say. So you need a specialized design and a lot of data analysis algorithm to decipher the signals. This can be very much used in almost all the monitoring for measuring almost all different types of parameters in structures. But they are mainly used for strain measurements in commercial applications. So all the other parameters they have done in the research level, but commercialized in the commercialized space, they are mainly used for strain measurements. Then electrical resistance probes. These are probes which measure the electrical resistance of the concrete, and based on this we can predict how much is the chloride penetration, whether crack has occurred, like that. So this is mainly based for mainly for durability monitoring. Then electrochemical sensors. Electrochemical sensors are nothing but corrosion sensors. These are embedded inside the concrete, and they are used to monitor how the potential of the steel varies based on the ingress of chlorides or ingress of moisture, etc. So these are the this is just a gist of what are the different types of sensors available in in commercial space and in research space. Now we will go deeply into some of the sensors, and then we will go to the case study. So some of the very specialized sensors are also available for internet purpose. So we can research in the market if we have any specific needs. How does the sensor works? First, we have to install the sensor inside the specimen, or it can be a bridge element, or it can be any kind of structure. So once we install the sensor, it will start emitting data. So this data is collected with the help of a data logger, and this data logger can be either connected to a cloud platform for this kind of data can be accessed from anywhere if it is uploaded to a cloud platform, or it can be directly given to a data receiver. So once we have this data, we have to do a signal processing. So based on this needs a lot of background in computer algorithms and how we should do the signal processing. So it is more of like you can sense that this is a multidisciplinary. Once even the signals, how we are getting the signals, it can be in the form of wavelength, or it can be in the form of some mostly it will be in the form of wavelength. It won't be having any direct number. Okay, so some waves, short waves and long waves will be generated. So this short and long waves should be processed to understand what is exactly going on. Without understanding the signals, we cannot understand what is going on in the specimen. So you can very well see this is multidisciplinary, and it needs lot. It contains a lot of logical based algorithms, as well as the sensor itself is consists of a lot of circuits, integrated circuits. Okay, so it in actual implementation of the sensor is in civil engineering structures, but when you look deeply, it consists of integrated circuits, data processing, as well as the coding. Okay, so all these skills are required for successful implementation of a sensor and structural health monitoring. So we have to do a lot of research in this space, which is currently lacking in civil engineering space. So the one who understands the signals do not understand how this data should be interpreted, and the one who understands the data, they don't know what is going on inside. So it's kind of a black box to the civil engineer. So this kind of gap creates a lot of friction in analyzing and understanding the data. So this is where a lot of research is needed. And once we do the signal processing, and we can go with the prognosis, what has to be done in the real time, whether we need to go for any repair work immediately, or we can wait, and how is the status of the damage. All these things will be sorry, all this sorry, all these things will be based on the signal processed signal. Sorry about it. Okay, so once we have this kind of, this is the base of sensor network. So once, it's not just getting a sensor and putting it inside the concrete. It involves a lot of other space also, like we have to go for a data logging, and then data analysis, mainly signal processing, and then how to do the interpretation of data. All this involves the structural health monitoring. Okay, so once we have the sensors inside, we have a lot of different things coming on from the information coming out of the structure. But before analyzing the results, we have some of the principles which we have to keep in mind for this, for coming to a conclusion. So they have listed some 8 axioms for structural health monitoring. The first is like all the materials have inherent flaws or defects. This is very well understood. None of them is ideal. So all the materials will have some defects. Okay, and then We cannot say, okay, now my signal is this and my reading is this, so this has been deteriorated. No. How we have to do is, we have to always compare between the states, like how it was in the beginning and how it is now. So it is always a comparison between two states. Okay. So you have to compare the system with the previous state and then previous state, like that. So you need to have a continuous monitoring and analysis, and you have to always compare with the previous state to understand how the damage has progressed, whether it has the damage is progressed or whether it is in the same set of deterioration. So we cannot have an absolute number or absolute terms in how we interpret the data. Okay. And a third is with the structural health monitoring system, there are like distributed systems on point-based system. So when you have a structural health monitoring system placed in like big structure, what we can do is we can understand from the data that there is a damage and the location of the damage, but we do not understand how severe is the damage or which type of damage. So if there is a crack, for example, they have the signal will transmit the data, and based on that we know that there is some deterioration, but we do not know whether the crack is continuously active, it's growing, or whether it is stagnant, and what type of damage caused this cracking, whether it is a differential settlement or because of the load or any other impact, or we do not know what exactly caused this. So we need to go to that particular site and then we have to analyze it. We just know that there is a deterioration happened because from the sensor network. Okay. So for localized and depth of analysis, we need to go to the structure and see what exactly is the damage. And then and one more main thing is sensors cannot measure damage. It just transmits us signals. We have to analyze the data and we have to come up whether this is a damage or not. And then
देखो है क्या? से ले लो चाबी, उसके अंदर ही होगी चाबी, वहाँ होगी.
I'm hearing noise actually. Am I?
Ma'am, we'll correct it now. Ma'am, is it okay now?
Yeah.
Okay.
Okay. So there is always a trade-off between the sensitivity as well and the damage measurement. So like if it is more sensitive, we will have more noise. So we have to come up with a noise to signal ratio and to have the meaningful data. So these things we should agree beforehand how we should analyze the data, because as I told you, the signal processing is done by different kind of engineers. So if we are not agreeing to the level of the signal to noise ratio, they will have some data analyzed in some form, and how they are giving it to us will not reflect what we want. So we have to come up with a resolution and sensitivity level to interpret the data. So always there is a trade-off. That is what is more emphasized on Axiom 6 as well. And the size of the damage, how big it is, changes the dynamics. Okay. So this is inversely proportional to the frequency in which it gives the excitation. So all these things should be kept in mind while analyzing and interpreting the data. So once we have different types of sensors, and we have how to put the sensors in place, how to do the algorithm, and then what is the thing we should keep in mind when we are interpreting the data. So we will go in depth into different types of sensors that are commercially used. The first one is temperature and maturity sensor. You can see here it can be as simple as a thermocouple. Thermocouple are two wires connected to each other, and based on the difference in temperature between these two wires, a voltage will be triggered. And this can indicate how much is the temperature that is going on is inside the concrete. So this can be there are different types of thermocouples. So this can be as simple as a thermocouple, or it can be radio frequency based. So where you have a transmitter and a receiver, and based on the frequency and amplitude, you can decide how much is the heat of hydration. Okay, from the heat of hydration, you can project the strength based on the maturity method. There are different maturity methods available. So what is more applicable to your site, you can use that maturity method. These kind of sensors are mainly used for finding the stripping time for formwork. So we have 7 days we will leave as a thumb rule for stripping time. But in very big projects, these will be a liability because they will be hiring this formwork, and the amount of time it is inside the site, as well as the delay in work because of the stripping time can be eliminated with these kind of sensors. So these are very much used in most of the sites in foreign countries, but I'm not sure whether this is used in India. But most of the projects which are mega projects are using this here. So the next sensor is temperature and humidity sensors. First one was temperature. It can measure only the temperature, but this type of sensors can measure both the temperature as well as the humidity. What is the advantage? Because when these kind of sensors are placed inside the concrete, it can also monitor the humidity. That means based on the climatic condition, if there is a change in the humidity level, we know that it will take some more time for setting. For example, if it is a cold climate, if it is below 5 degrees Celsius, we know that the concrete cannot set. So when such concreting is happening in such kind of climate, we have to wait for some more time to attain the required strength. So such kind of information will be available from this kind of sensor. Then we have something called electrical resistivity sensor for concrete. This is done on the cover. You can see that there is a reinforcement, and then it is placed on the cover. Okay, so when the concrete is poured, and it will be in the level of concrete itself, and then when chlorides or any other deteriorating agent is ingressing in the cover concrete, the resistivity of the cover concrete changes. So when the resistivity of the cover concrete changes, we will know that there is some kind of deterioration that is happening. So for example, if chloride ingress is taking place, that time the resistivity decreases. So this means that you can measure how, there are different layers in this. Okay, so if the you can see my cursor, right? So this is the surface. These length will be embedded inside the concrete, and when the chloride ingress progresses, you know that the resistivity decreased up to this level, and when it moves further and further, you know that the chloride penetration is happening slowly, and it is going to reach the steel. So based on this kind of information, we know that whether my when my steel is expected to be initiated, and you can take some precautionary measures. For example, when the steel, when you have any other type of deterioration, that time also it will eventually lead to corrosion. So you know that your concrete is prone to corrosion or not, and what type of corrosion. For example, this will tell us that whether it is a chloride ingress corrosion, or if it is in case of carbonation, there will be a resistivity gain in the initial phase, and then it will go to the cracking, and then it will indicate a different type of corrosion. So all this information can be obtained from this electrical resistivity. And this is a specialized sensor. So this is called a corrosion sensor. What it will do is it will measure the potential of the steel, and then it will give us the direct value. How much is the potential difference between the embedded steel and the embedded sensor? Okay. So we have some standards which says that if it falls in this range, then that means the corrosion is more likely, or if it is in this range, then corrosion is not happening, like that. So there are different types of sensors. This is like point-based sensor. At specific points you can install and monitor the potential. And this is Muir sensor, which is like continuous sensor. It is a continuous wire kind of thing, and you have to place it near the tendon, and it has some specific intervals at which the sensing points are located. So you know that at this point it is it has started corroding, so like that. So this is a very stable sensor, and it can be used for long-term monitoring. So the main issue with these all these sensors are like they are more robust and more reliable during the initial phase, but once it crosses some 3 months or more, then it will start deteriorating. The sensors are not reliable anymore. So the longevity of the sensor is always questionable. To ensure the longevity, we have to come up with innovative ideas, and we have to see how it can be prolonged. For example, this sensor, there will be a problem with the reference. Like the wire can be polarized, and it can give to lead to erroneous conclusions. So how to ensure that what we are getting from the sensor is reliable, as well as how to process the signals that are coming from the sensors. These are two main research areas where a lot of research is needed, as well as we have to implement more and more in many of the structures to understand the real-time issues. I'm sorry about my voice. Suddenly it happened. Apart from the specific sensors, we have till now have seen specific sensor. For example, it is whether it is used for temperature, whether it is used for corrosion, whether it is used for electrical resistivity, like that. There are technologies available which can be used for measuring multiple parameters. So these are multi-parameter sensors. In that, the first is RFID based. You might have heard that in US, when the Indian students went, they were given an RFID tag and they were tracked. Yeah. So this is the similar sensor, but it's not for tracking people. It's for tracking the deterioration. It works on the principle of radio frequency. So there will be two main components. One is called receiver, that is the reader, which reads the signal from the tag, that is the transmitter. Okay, the transmitter will be embedded inside, and the reader, when we go near the tag, it can read, and it is like how you do a barcode. When there is a barcode, the signal picks up, and it just displays the cost, right, in the grocery shops and other things. Similarly, this tag, when you put the reader near the tag, it receives the signal from the tag, and it transmits the signal. So these signals have different frequency and different amplitude based on the type of deterioration. For example, if there is corrosion, it will have a different frequency and amplitude. If there is no corrosion, there will be different frequency and amplitude. Similarly, you can measure strain, you can measure humidity, you can do many parameters with these type of RFID sensors. This can also be passive or active. For active means it is connected to a battery, and it is always in action. Passive means whenever it is needed, it will transmit the data. That is, when you take the receiver to the tag, then it will sense. Otherwise, it can directly, if it is active, it will start emitting continuously. Okay. So these kind of RFID sensors are very, very, it can be designed to like, if you can see, this is like a size of the matchbox. Okay. So if it is an active system, it will be connected to a battery, and the circuit which is designed for this active system, it can last for like 1 to 3 years, maximum up to 5 years if it is based on semiconductors and other circuits. But if it is a passive system which does not involve battery, so that time you can have a extendable life, but installation of such system is very, very laborious. You need to have a very expert, you need to have so much of expertise when you have such kind of system placed. So this is based on RFID. And the next one is FiberGrating Sensors. It is called FBG Sensors. It works on the principle of optics. You can say that it can be used for both point-based as well as distributed systems. Point-based are like at specific points you install this kind of cables, and then from that it will sense. And distributed is the whole cable is a sensor. Okay, so the cable is etched such that it will emit only a particular wavelength, and it will transmit only, it can reflect back only one particular wavelength. It reflects back all the other wavelengths and transmit one particular wavelength. And this wavelength will change based on the strain and temperature. Okay, so the shift in wavelength is analyzed with the help of scattering principles like Rayleigh scattering, Boolean scattering, like that. And then when we analyze the data, we'll get what is the signal that is coming out, and we can decipher the signal. This is very, very powerful and robust. It can be used for long-term monitoring, but it is very, very costly. For installation of this FBG in a particular structural element, you need at least minimum 10,000 pounds in UK. So you can imagine the amount of money we have to invest in as an initial investment. And this kind of investment should also justify why we are doing it, right? The structural health monitoring, the amount of money we are investing, there should be a ROI. That is where it is lagging now because of the long-term robustness which is lagging in these kind of sensors. So we have to invest more and more on this sensor development as well as the signal processing algorithms, so that it will be accessible for all the countries in all kinds of projects. So now I'll come back to this FBG. So here, when you install, because the whole cable is a optical sensor, we have, if there is some pinching that happens, for example, if there is during we might have installed this, and during concreting somebody steps on it, or during the bar bending, if we are keeping something on top of it, there will be a pinching happens. So it based on, since it works on the principle of transmission, that kind of pinching will affect the data. So we have to have very careful installation. So these are the precautions we need to have when we use this fiber optic sensors. But this is very, very reliable. Once installed, it is very, very reliable, and it can be used for long-term monitoring. And it can also be used for multiple parameters like strain, temperature, tilt, acceleration. Then it's now in used for finding even the carbonation, all those things. Commercially, it is mainly used for strain measurements, especially in piles. So we do not know how the how good is the pile, the concreting that has been happened, what is the strength, whether it is in place, proper in place. All these things can be monitored with the help of these sensors. So here in UK, a lot of implementation has been done for pile measurements. Since it is also not accessible very easily, how you will test the pipe? You can load and then you can monitor. But other than that, if it is not a pile load test, how else you can monitor? You cannot monitor in other means because it is in the foundation, right? So this fiber optic sensors are particularly useful in such cases. And also the tunnels, where you do not know how, there will be a lot of inaccessible areas. So in that case also, you can use this fiber optic sensors. Then the next one is acoustic emission sensors. So these are like works on the principle of sound. So when there is a crack formation or any kind of deterioration, some kind of sound waves happens. So these sound waves are captured by the sensors, and from that signal we can analyze, and then we know how the deterioration is happening. These are very much used in case of pre-stressed and prefabricated concrete. And these are the different types of sensors that are available in commercial market. So all these fiber optic sensors, acoustic emission sensors, RFID sensors, these are like, there are specialized agencies which does this for us. Okay, so it is not like we buy and we install on our own. Since these involve signal processing and the data collection, first the sensor installation, then data collection, then signal processing, all these things are very specialized forms particular to that kind of technology. Okay, so there are specialized agencies for this, and they will charge us a lot. So these, we have to come out of the monopoly of these agencies. So we have to do a lot of research in this area, and we have to encourage interdisciplinary research. I'm telling every now and then, because even I am facing this issue. When I go to a agency, they will tell that this much amount of money is needed for implementation of this. So we cannot negotiate in terms of any other thing other than reduce the cost. We do not know how the data is processed. So we are very much, it's like a black box. Once we get the signal, we will interpret, okay, maybe it could be this, it could be that, like that. But before that, what is happening? How my structure is being analyzed? We have to have that kind of knowledge also. So we have to encourage our students for such kind of interdisciplinary research. When I started my civil engineering, I used to think that civil engineering means it's more like structures, concreting, bar bending, then estimation, like that. But when I started my course, I didn't have any idea that civil engineering is interdisciplinary to the highest level. If you see the basic engineering forms, civil engineering, whatever is happening in and around you, all of them will be accommodated in civil engineering. And civil engineering has principles which can be used from like aerodynamics to signal processing. Everything can be accommodated in civil engineering. So I'm emphasizing once again that we should encourage interdisciplinary research and interdisciplinary thinking in our students as well. So next is challenges. The sensors which I have shown, most of them are embedded sensors. So these embedded sensors, we have a severe challenge in the robustness. As I mentioned, there are a lot of things which we need to experiment more on in the space. How we can prolong the longevity of the sensors, and then ease of replacement. For example, the fiber optic sensors, you have to design the fiber optics, and then before the installation, we have to verify whether the sensing unit works fine. And then we need to take so much precaution before concreting. So all these things are time consuming as well as very costly. So it should not be too much technicality should not be there, and it should be accessible to all people who wants to do this. So there should be ease of replacement. And designing the sensor layout is again very challenging. And then if it is not embedded, so if it is surface mounted, the number of sensors required for getting the same amount of data as that of embedded sensors varies because it's on the surface. So we need to understand how many are needed for getting the level of data. And when you have installed such kind of sensors, we have to also protect it from vandalism. So these are the things we need to consider when we are installing the sensors. Then, as I told you, it is like a black box. They will analyze the signal and give it to us, but we should know how to interpret the data. So there is a trade-off between the sensitivity as well as the noise. So we have to see how to increase the signal to noise ratio for better processing of data. And then there is always a software and hardware integration. The sensor is a hardware part, and then when you get the signals and process the data, and it comes to the engineer for interpretation, it is more of a software analytics. So hardware and software integration is very much needed. So in general, after all this, what I think is the biggest challenge about the implementation of sensors is how to do the data interpretation. When we get the signal, we will process it, and then from the processed data, how to do the interpretation. Where is my structure standing? What are the next best actions? These are the main challenges which we face. So I will conclude it with a case study. So this is a case study which where I worked for nearly 6 months for data collection and things like that. So I will talk more about this in a minute. So this is underground metro construction. Why this is structural health monitoring is needed during the construction of underground metro is the main motivation is asset protection. So when you start digging from beneath, it should not disturb the structures which are already there. So existing network and other assets should be protected, and we should know if there is any deviation that is happening. And also there are some ground movements that will happen during tunnel boring, because it's a huge machine and it starts boring from beneath. So there will be a lot of ground movements, and we should ensure that these ground movements do not affect us adversely. And since it is beneath, there will be underground water level and also the seepage associated with it. So we need to take care of that, as well as we have to maintain the verticality. If there is a underground construction, there will be a diaphragm walls, and the diaphragm walls we need in perfect vertical line, so that it doesn't waste our money. So these during construction prevents liabilities and also the delay due to untoward incidents. This is the main motivation behind using a SHM. So imagine this is the underground station. So this, you can see that there is an underground station here. This station, usually it is constructed as a diaphragm wall in case of soft soils, and you can have piles or a continuous wall in case of hard rocks. And then between the stations, you bore it using the tunnel boring machine. So how you will do this tunnel boring, how you install the tunnel boring machine is through the shaft. So from the ground level, you will have a big pit excavated, and from the pit you will lower the tunnel boring machine, and from the machine you will drag it to the site of intention. So these are considered underground stations are constructed as individual entity, and the tunnel boring machine connects these stations. So every underground station will have like a bell mouth to receive the tunnel boring machine, because there will be a huge impact when the tunnel boring machine comes. There will be a huge impact. So to take that impact as well as to maintain the stability, we have a bell mouth opening here. And this shaft, as I already told you, is for assembling the TBM. So the underground station cross section will look like this. There will be a top slab, concourse slab. Top slab is which supports the soil, and concourse slab is like there will be a landing between the entrance and the station. So that will be a concourse slab, and then the tunnel will be there, where there will be a base slab. Base slab will act as a platform, and beneath that we have utilities for drainage, electricity, vibration, etc. So these are excavated and lined with concrete. So as I mentioned, the underground station, first activity is the Dwall construction. So we can have either, this is called hydraulic grab, and this is called a hydraulic cutter. Grab is used for soft soil, and this is used for hard soil. When we have this kind of excavation, it's like 30 to 40 meter deep, and we do not know how vertical it is. So to understand that, we need to there is a test called Codon test. It is similar to the plumb bob. Here you can see in plumb bob we see visual inspection, but here the ultrasonic sensor will go directly to in the pit, and it will sense and record the wave. So the trench wall verticality can be determined with the wave thing. Next is the station box. So here, once you construct the diaphragm wall, you can see the wall, then you will start excavating. This is called top-down approach, where you excavate the soil from the top, and then you reach the required bottom. Okay. So in this, we have to install different girders, studs, etc. to maintain the stability of the diaphragm wall. Since you are excavating here, suddenly you have to maintain this pressure, okay? Pressure in the side, pressure in the diaphragm wall. For that, you need to have supporting structures, and these structures you need to also monitor because these are huge structures and we are excavating. There will be a lot of difference in the load that is coming into these temporary structures on different stages. First, when you install, there will be a different load, and when you start excavating from beneath, there will be a different load. So the structure should be monitored continuously, so to assure the stability. Okay, so there are different types of sensors like load cells, borehole extensometers, and then strain gauges, accelerometers. All these are employed to understand whether there is a movement, whether there is a strain increase in the temporary structure. So when there is a strain increase, there will be indication. Then we can have a proper additional support installed in such kind of places. Then shaft. When you install the shaft, the lining of the shaft will be subjected to different stresses. So to understand that, we can have a LVDT, or we can have an extensometer, or we can have a strain gauge, and the strain gauge can be electrical, vibrating wire, or FBG, like that. So when we install the concrete lining, we can have these installed together so that we can monitor in a long-term basis also. When the tunnel is getting, the tunnel boring machine is in operation, there will be a lot of stress induced on the side of the tunnel. For example, there can be a differential settlement. If there is a high-rise building near to the tunnel, there will be if a small settlement happens, it will induce a crack and it will question the stability of the high-rise building. So in such cases, we need to monitor it very, very closely. So this kind of tilt meters and inclinometers are installed near to the line, the tunnel boring line, so that we will know whether there is any damage that is occurring to the existing foundation, or is there any kind of settlement that is happening. And also we can install the pore pressure meters, where the soil seepage and groundwater movement can also be monitored. If there are any leaks, that also can be monitored. The pore water pressure will say how much is the water pressure that is happening, and leaks can also be detected with the help of fiber optic sensors. Then as I mentioned before, the corrosion of reinforcing steel and cracks measurement, these are all long-term. These instrument sensors are installed for long-term monitoring, because these tunnels, once we install the linings, it's very, very difficult to access. So if we are aiming for long-term monitoring, these sensors should also be installed during operation. So in summary, structural health monitoring is useful and beneficial when there is actual ROI. So we need to understand how much we are investing and how much returns we are getting. That is the main motivation of the owners. So we need to ensure that. And in addition to this, we have increased the safety and reliability, low maintenance cost, and better understanding of the built environment, because we always know that we design based on some assumptions, but the reality of the location and reality of the structure can be different. So to understand the built environment better, these kind of structural health monitoring will be very, very useful. And there are two types of approaches. One is traditional approach, where we are using NDT methods, and the modern approach, where we are using different sensor networks. And a case study is also presented, like where we can use these sensors and how we can use the sensors. So when we use the sensors at the right with the right approach, then it can give a maximum return of investment, and it can be given more and more information to eliminate sudden collapse. So we need a lot of research in this space for a better future. So questions?
Participants, you can unmute and interact with the expert.
Some of hand raise has been seen in the chat box. Please unmute your mic and your doubts. Dr. Ramakant sir. Please unmute your mic. Participants can ask questions in the chat box also. Okay, please put your doubts in the chat box also.
I know I rushed a little bit to accommodate a lot of things, and actually this is quite heavy topic if you are not very familiar with sensors. So I try to introduce some of the basic things which we do for structural health monitoring. But as you go deeper, you will understand that a lot of things are very much needed for our current problems. What we face in different kinds of structures like bridges, then high skyscrapers, like that. Now, whatever we are building, like bridges and other things, they have like a service life of 100 plus years, and they mandate the structural monitoring and contract documents itself in foreign countries. Wherever they have 100 plus years requirement, they are mandating that. So I hope India will also move towards it, and we should be better prepared for this kind of challenge that we are going to face. So my main motive of this presentation is we have a lot of sensors in the research stage, but it is not being commercialized, or it is very costly when it is commercialized. So we need to work in a space where it can be affordable as well as useful and affordable. When it becomes, then it will be used more and more in projects, and it can yield better results. So I hope it ignited some of the thinking in your minds. So I'm just waiting for questions. If you do not have any questions, then we can wind up also. I'll wait for another 10 minutes. Please feel free to have question. I think I have a question.
Chat box.
Yeah. I'm reading one question. What are the major things to carry SHM concept in pre-stressed structures or truss structures? Pre-stressed concrete means we need to have, as I told, we have to have some embeddable structures, and pre-stressed concrete acoustic emission will be very, very useful, because the acoustic emission will produce a kind of noise, one kind of sound when the cables start breaking. Even one wire of the tendon, if it breaks, then it gives a clear indication of the sound. The sound gives a clear indication of breaking of wires, and it can be interpreted where it is like we can locate the area, and then we can take the mitigation step. So acoustic emission has been proven to be very, very useful in case of a precessed concrete structure. Yeah.
Any other questions?
Sorry.
Participants, please ask. Ma'am, somebody for a PPT. Some participants are asking for PPT. Can you share the PPT for the program?
Yeah, I can share it with the organizer, and from the organizer you can take that. Is there any data set available for public domain or research? Unfortunately, I'm not aware of such data set. It is more of the, as I told you, these are specialized, there are specialized agencies which does this kind of implementation for you, for your site. So they will analyze and they will give the data like that. There is no data set as such available according to my knowledge. Yeah. And they will charge quite a lot. So I encourage all of the civil engineers to learn different skills like coding, like machine learning, and these things, so that you can very well analyze your own data. Signal processing, maybe that will be too much, but still anything can be learned. So I encourage all of you to do interdisciplinary research, and construction is becoming more and more advanced, and sometimes it feels like, oh, is this civil engineering or is this something else? Like that, you will be amazed with the type of research everybody is doing and everybody is implementing in their sites. So we should come out of the typical mindset with it's not, civil engineering is not only about estimation and costing and being a site engineer. It is very much part of it, but it has moved from that to a very wide umbrella. So I encourage all of you to do interdisciplinary research, and you just go and talk to different engineers. You will get a lot of ideas about how you can do different things in your own area. You can now, research is not purely fundamental. It is more about thinking and interconnecting ideas. How you can interconnect one idea from one discipline to the other discipline. That is more prevalent today, and we can easily implement that also. So if you can collaborate and do interdisciplinary research, it will be great.
Thank you, ma'am. Thank you for your very informative session. We hope that some of our participants will surely take up some new ideas and do interdisciplinary researches. Now, I welcome Christy Francis Lond for the vote of thanks.
Thank you, ma'am. So it's my privilege to have been asked to propose a vote of thanks on this occasion. I, Christy Francis Lond, on behalf of the Civil Engineering Department, College of Engineering, Kidangoor, extend a very hearty vote of thanks to our expert, Dr. Sri Priya Rangaraju ma'am. for not only sparing your valuable time for us, but also for enlightening us with a commendable talk on structural health monitoring. Thank you, ma'am, for sharing your findings with us. I'm confident that from this session, the participants were able to glean the vital information about structural health monitoring, where she clearly explained about its needs for what type of structures it's used, its traditional ways of structural health monitoring, some of the modern methods and its challenges also were explained by her. Among all the sensors, I especially like the modern methods where she explained about continuous structural monitoring using sensors and sensor network. Apart from specific sensors, some multi-parameter sensors like RFID based battery operated embeddable sensor for concrete and also FBG sensors which can be used for long-term monitoring was explained by her in this session. She concluded her session with a case study on underground metro construction where the usage of sensors were explained clearly by her. Ma'am, thank you once again for enlightening us with the information and knowledge in structural health monitoring. Thank you so much, ma'am.
Thank you so much for having me in this occasion. And thank you all. Thank you very much for the participants as well and the faculties who provided me with this opportunity. Thank you.
Thank you.
Dear participants, we will join for the next session at 2 o'clock.